Back. So now we start section 6.3 logarithmic functions. Recall, for base b greater than 0, b not equal 1, you have the exponential function fx equals b raised to x. This function has the following graph. When base b is greater than 1, it's an increasing function, okay? Y-intercept is 0, 1. When base b is less than 1 but greater than 0, so remember our base is greater than 0, not equal 1. So when base b is between 0 and 1, exponential function is a decreasing function with y-intercept 0, 1. Notice these two graphs, they pass the horizontal line test. That is, any horizontal line on the positive y-axis will intersect your graph only once, exactly once, right? So the exponential function for base not 1, okay? Remember, when base equals 1, your exponential function is a constant function. So it's important to remember that exponential function is 1 to 1 when base is not 1. Base is, of course, greater than 0. All right. The exponential function for base not equal 1 is a 1-to-1 function with domain negative infinity to infinity, range 0 to infinity. Domain negative infinity to infinity. For every x, you have the graph above it, right? Whereas the range, the entire values are on the top half of the plane. So range is 0 to infinity. So these are the exponential function for base not 1, base positive is a 1-to-1 function. So first definition, let base b be greater than 0 and base not equal 1. The logarithmic function with base b is the inverse function of the exponential function. Fx equals b to the x. The inverse function, f inverse, is denoted by log base b. That's how you read it. Log base b. So exponential has a certain base. Its inverse has the same base. That's how it's denoted. So what is log base b? Well, it is a function which, you see, inverse function has domain, that is the range of your original function. Okay? So log base b starts from 0 infinity and maps to negative infinity to infinity. So your exponential function has domain negative infinity to infinity. So the inverse function has a range negative infinity to infinity. Exponential function has a range 0 infinity. So your inverse function log has domain 0 infinity. So what is log base b? It is a function from 0 infinity open to negative infinity to infinity open. It is defined as log base b of number x is y if and only if b to the y is x. Okay? So whatever y was taken under exponential to x, so you have flipped it. That's what has happened. Okay? Now, you have the following properties. One, log base b of b to the x. So in other words, take any x. First take its exponential, then take its log to the same base. You get back x. That's the meaning of inverse, remember? Now, this happens for every x in the real number line because exponential is defined for every x. On the flip side, b to the log base b of x is x. This is also inverse function. So first log and then exponential is x. Now, log base b is defined for only positive numbers. So x has to be in the set of positive numbers. All right. So here are a few examples. As 3 to the 4 is 81. We have log base 3 of 81 is 4. You see, this is exponential, this is logarithm. So 3 to the 4 is 81. So log base 3. So base is 3, right? And that's what the log base b has to be. So log base b of 81 is 4. Likewise, 2 to the 5 is 32. Base is 2, so log base 2 of 32 is 5. 1/2 to the power 3 is 1/8. So log base 1/2 of 1/8 is 3. 1/3 power 2 is 1/9. So log base 1/3 of 1/9 is 2. So notice what's happening here is, for instance, if you just looked at this, log base 3 of 81 is 4. So what are we doing? We are looking for the power of 3 in 81. Log base 2 of 32 is 5. The power of 2 in 32 is 5. Okay, so precisely. Here are a few graphs of log. So log base 2 is the blue graph. Log base 3 is the red graph. Log base 1/3 is the purple graph. And log base 1/2 is the green graph. How do you graph this? Look, log base 2 is inverse of 2 to the x. So you need to draw 2 to the x and reflect it, and that gets you log base 2, and so on and so forth. Notice, higher the base, for base greater than 1, higher the base, slower the growth. Okay, log base 3 is lower than log base 2 after 1. All right. So keep track of what's going on. Here is log base 1/3 and log base 1/2. So 1/2 is smaller, but they are both negative. Not negative, I'm sorry. They are both less than 1. So 1/3 is smaller, 1/2 is bigger than 1/3. So you see, log base 1/2 is steeper. Okay, so do keep in mind what's going on here. All right, properties. Let's look at the properties. If base b is greater than 1, for example log 2 and 3, then the log base b is an increasing function. Okay, they are increasing functions. Further, as x approaches infinity, log base b is positive infinity. So as you go far away to the right, these functions are increasing slowly, but they are increasing. So over time, they'll go to infinity, positive infinity. Whereas as x approaches 0 from the right, my log starts going to negative infinity. All right. So this is when base is greater than 1. So these are your two examples. What happens when base is between 0 and 1? Here, my functions log base b are decreasing. Okay. Further, as x approaches infinity, log base b of x is negative infinity. They are going down. Surely, even though slowly, they are still going down. Therefore, they go to negative infinity. As x approaches 0 from the right, as x approaches 0 from the right, these functions go to positive infinity. So in either case, base greater than 1 or base between 0 and 1, you have y-axis to be a vertical asymptote. Okay, so let's continue in our next video.